Welcome to section 14.3. Alright, gentle people, to start off this lecture, what I want to do is get us some practice drawing molecular orbital diagrams. So we're going to focus on homonuclear diatomic MOs. And so what that means is I want to try to go ahead and draw the MO diagrams to Li2, Be2, B2, and so on across that second row on our periodic table. So let's go ahead and start out with Li2, or dilithium. So if you guys are a fan of Star Trek, they mention dilithium crystals. So let's go ahead and see if dilithium is something that is theoretically possible. So that means I'm going to take a lithium atom and combine it with another lithium atom. Now let's go ahead and draw the atomic orbitals of lithium. I have a 1s orbital, and in the 1s orbital, I'm going to go ahead and have 2 electrons. Now, lithium has a third electron, and this is going to go into the 2s orbital. So if I want to draw my 3-panel picture, I'm going to draw this second lithium in the same manner. Now, in the middle, I'm going to go ahead and draw my Li2 molecule. And so what I'm going to do is with the 1s orbitals, I'm going to do what I did last time. I'm going to put them constructively together and destructively together. I'm going to do the same thing with the 2s orbitals. So remember, the 2s is just a bigger version of the 1s orbital. So I can go ahead and combine them constructively and destructively to get my molecular orbitals. So in this case, I'm going to make something that's sigma, made from the 1s, something that's anti-bonding, made from the 1s, and then I'm going to make another sigma, and this one is going to be made out of 2s orbitals, and a sigma star made from 2s orbitals coming together. Now in this case, I have 6 electrons. So I'm going to follow my 3 rules, 1, 2, 3, 4, 5, and 6. Now I can calculate my bond order. And so for my bond order, I take a look at my bonding electrons. So 1, 2, 3, and 4. And then I'm going to subtract my anti-bonding electrons. So minus 2. I'm going to go ahead and divide this by 2 because of the formula. And then what I get is a bond order of 1. So based on MO theory, what we see is dilithium is predicted to exist, and that dilithium is going to have a single bond between the 2 atoms. Now what I want to mention with this picture is this is the way that Alex does these types of molecular orbital diagrams. What they are doing is they are using all the orbitals with all the electrons. And what I mean by that is all means I'm using the core plus the valence. Now there's a shortcut to do these diagrams, and this is what your book does and what you will see in a lot of other places. And what we can notice is that things in a different shell don't interfere with another shell, meaning everything in n equals 1 is not going to interact with things in n equals 2. But what's more is if we look at core orbitals and core electrons, they cancel each other out, meaning the number of bonding electrons is the same as the number of anti-bonding electrons. What a lot of methodologies use is just to look at the valence electrons and the valence orbitals. And what I mean by that is they'll take lithium and try to combine it with lithium. But in this case, I'm going to look at the valence orbitals and the valence electrons. So the valence orbitals for lithium is 2s with 1 electron. And so to make dilithium, I'm going to go ahead and constructively put these 2s orbitals together and destructively put these things together. What I'll get is a sigma 2s and a sigma 2s star. Now, if I count the number of electrons I have to use, well, I have to use 2 electrons. And so if I do my bond order in this case, I have 2 bonding electrons, There is no anti-bonding electrons, and I'm still going to divide by 2. And this still gets me a bond order of 1. So when you do this method, this is the book method. And again, in this method, what you're going to do is you're going to use the valence orbitals with the valence electrons. And you guys will get the same answer. The only caution that I have with you guys is you have to be consistent. So if you are only using valence orbitals, you have to use just the valence electrons. If you use the valence orbitals and then start using all the electrons, you're going to get the wrong answer. So be consistent. All right, let's go ahead and do diberyllium. And let's do it the book way. So I'm going to use the valence orbitals, which is the 2s, and it has 2 valence electrons. I'm going to do the same for the other beryllium. I'm going to put the molecular orbital for diberyllium in the center. I'm going to get constructive interference, destructive interference. So sigma 2s, sigma 2s star. In this case, I have 4 electrons that I need to fill my molecular orbital diagram with. 1, 2, 3, 4. I can go ahead and calculate my bond order. I've got 2 bonding, 2 anti-bonding, and I'm going to divide by 2. So I get 0 for my bond order. And again, this molecule doesn't exist. So let's move on to the next element in the periodic table. Let's see if we can make B2 diboron. For boron, if I look at the valence orbitals, I'm starting to fill out the p orbitals. Up until now, I've been talking about how s orbitals mix and match. So now what I got to do is figure out how p orbitals are going to mix and match. So let's go ahead and take a look at this side of this slide. What you guys will see is me combining orbitals in n equals 2. Now what I'm going to do is express the phase of the wave by shaded and unshaded. So in this case, what you guys will see is that I have 2 s orbitals coming together, and they're both shaded, meaning they are in the same phase. So this 2s orbital comes together with this 2s orbital, and this is my sigma 2s. Now if I bring them out of phase with each other, so this is shaded and unshaded, well, this is my sigma star 2s. And we already talked about how 2 of these 2s orbitals are coming together to form molecular orbitals. Now what I want to do is try to bring in our p orbitals and see how they combine and how I can mix those orbitals to generate molecular orbitals. Now there's a couple of things you have to understand before we talk about this. So remember, the p orbital is dumbbell shaped. Now each one of these dumbbell lobes are in a different phase. So what you have with a p orbital is 1/2 of the p orbital is shaded and the other half of the p orbital is unshaded. Now remember, our p orbitals come in 3 different orientation: x, y, and z. So in this case, what I'm going to say is the z p orbital is going left and right, the y p orbital is going up and down, and the x p orbital is going in and out of the page. So let's go ahead and see what happens when we combine a pz with a pz. So here are the nucleuses of my atom. I'm going to go ahead and draw my pz orbital. Now remember, my pz orbital is going to be a dumbbell shaped, and it is going left to right. Half of my orbital is going to be shaded. Let's go ahead and say that we're going to combine these 2 pz orbitals together. What you guys will see is as I bring these 2 orbitals together, these will be in phase. That means when they come together, they're going to enhance the probability of having electrons between the 2 nuclei. So combining these 2 pz orbitals results in an orbital that looks like this, where there is an increased probability to find the electron between the two nucleuses. So if there's an increased probability of finding electrons between the nucleus, we consider this bonding. And if I were to rotate this around, the bonding axis, which is the line between the two nucleuses, what we would see is that this is sigma in symmetry. So taking these two pz orbitals together gets us a new orbital. This orbital is sigma in symmetry and is made from two p orbitals. Now there's another way that I could have combined this. I could have taken the pz orbital off of one atom and combined it with the pz orbital of the other atom, but I can go ahead and combine them out of phase, meaning I'm combining the shaded with an unshaded. This is going to cause destructive interference. When I put these two orbitals together, the destructive interference is going to cancel out any probability of finding the electron between the two nucleuses. So this picture up here is going to be an anti-bonding orbital. Now I can go ahead and look at the symmetry of this orbital. Here's my bonding axis. I rotate around that, and what I see is it is symmetric with the bonding axis. So again, this is going to be a sigma type orbital. This is made from my two pz orbitals, so I'm going to call this sigma 2p star. So this takes care of pz's coming together. Let's go ahead and take a look at the other p orbitals. So again, I have my nucleus, and this time, let's look at py. So I'm going to take two py's and bring them together. Remember, our p orbital is half shaded, and so I'm going to bring these together. So when I bring these two py orbitals together, they're in phase, and so I will get a great enhancement of electron density between the two nucleuses. So this is going to be considered a bonding orbital. However, when I look at the symmetry of this, what you guys will notice is this is asymmetric with the bonding axis. When I spin around this bonding axis, I can go ahead and see the shaded and unshaded flip up and down. So I can tell that the orbitals are spinning. So if it's asymmetric with the bonding axis, this is going to be pi in symmetry. Now this molecular orbital was constructed from the 2p orbitals. So this is going to be designated as pi 2p. Now there's another way that I could have brought these two orbitals together. Again, here's atom 1 and atom 2. And these are my py orbitals that are going up and down. But this time what I'm going to do is I'm going to bring them together out of phase. So what that means is the unshaded and shaded are not going to match each other when I bring these waves together. So what's going to happen is that they are going to cancel the probability between the two nucleuses. So this is going to be considered an anti-bonding orbital. Now what you should also note is that if I look at the symmetry of this, again what you see is if I spin around that bonding axis, you can tell because of the shaded and unshaded that I'm spinning around that axis. So this again is going to be pi in symmetry and constructed from 2p orbitals. So this orbital is pi 2p star. Now I want you guys to go ahead and try to do the same exercise with the px. What you guys will find is that the px is like the py, where I will construct a pi 2p and a pi star 2p. Remember, the px is going in and out of the page, and you guys can refer to this last slide to see all the pictures of my orbitals coming together. So let's go ahead and put diboron together. So I'm going to make the B2 molecule. So first I need a boron atom, and the boron atom has p orbitals. So these are my 2p orbitals. There are 3 of them. It also has a 2s orbital. Now, since I only use the valence orbitals, I'm just going to fill up my valence electrons. So 1, 2, and 3 valence electrons for boron. I'm going to combine that with another boron atom, and it has the same atomic orbitals. So I'm going to go ahead and mix these atomic orbitals to form my molecular orbitals. So my 1s, constructive, destructive interference. This is going to be sigma 2s, sigma star 2s. Next, let's go ahead and combine our p orbitals. So the first set that I'm going to combine is I'm going to combine my py. My py is going to make a pi symmetry orbital, and this is constructed from the 2 py's. And this is the constructive interference. It is also going to combine destructively, and that's going to make the pi star 2p. Now, I told you guys that the px is going to do the same thing, and that's going to create a degenerate set of orbitals. So this is going to be the px coming together, and the px can come together destructively. Now, when the pz comes together, it's going to form a sigma bonding orbital and a sigma star. And so this is going to be the molecular diagram for B2. Now, I have to fill in my electrons. There are 6 electrons. So 1, 2, 3, 4, 5, and 6. So again, we have to follow our 3 rules. Alphabet, fill from the lowest to the highest. Polys, only put 2 in. And remember Huns, if you have degenerate orbitals, remember to put 1 in each before you start pairing them. Now, the one thing that you might be asking is, how did I figure out the energy levels to each one of these orbitals? Now, these were experimentally found out, so this is something that you're going to have to memorize or print out. Now, there are 2 schematics to use. One is going to be for lithium through nitrogen, and then the rest is for the rest of the periodic table. So that means oxygen and beyond. Now, the diagrams are very similar. You're going to have your sigma 2s, your sigma star 2s. Then is where the change occurs. For most of the periodic table, it goes sigma 2p, pi 2p, pi star 2p, and sigma star 2p. Now, for elements dilithium to dinitrogen, there's going to be a swap between the pi 2p and the sigma 2p. So again, to restate it, you're just going to flip the energies of these orbitals that I've boxed in red. All right, now that we have these diagrams, let's go ahead and try to practice them out so that you get used to filling out MO diagrams. So what I want you guys to do is tell me which has the strongest bond, O2, O2 plus, or O2 minus. All right, gentle people, let's go ahead and start drawing the molecular orbital diagram for O2. So I have an oxygen atom, and I'm just going to use my valence orbitals. So that's going to be the 2p and the 2s, and oxygen has 6 valence electrons. I'm going to do the same for the other oxygen. I'm going to make the molecular orbital diagram for O2 in the middle. To do this, I combine the 2s constructively, destructively. I do the same for my p orbitals. And so I note for oxygen, the way that it works out is that I'm going to have a sigma, I'm going to have my pi's, I'm going to have my pi stars, and then I'm going to have my sigma stars. And so I can label all of these orbitals. So sigma 2s, sigma star 2s, sigma 2p, pi 2p, pi star 2p, And then finally, sigma star 2p. Now let's go ahead and put in our electrons. So each oxygen has 6 electrons. So I'm going to put in 12 electrons into my middle diagram. 1, 2, 3, 4, 5, 6, 7, 8, then pair 9, 10, 11, and 12. So let's go ahead and calculate the bond order. So the bond order for O2. So if we count bonding, 1, 2, 3, 4, 5, 6, 7, 8. So there's going to be 8 bonding electrons, and there's 2 anti-bonding electrons here, and another 2 up here. So minus 4 divided by 2, so I get a bond order of 2. And this should make sense to you. O2 has a double bond between it. So now let's go ahead and do O2+. Now O2 plus looks the same. If I put a positive charge on my dioxygen, that means I remove an electron. So I'm going to take the last electron that I put in my picture. So if I go ahead and do these counts again, what you guys will still see is that I still have my 8 bonding electrons, but now my anti-bonding electrons, I have 1, 2, and only 3 here. So my bond order goes to 2.5. Now let's go ahead and look at O2-. So to do this, let's go back to our O2 picture. And this time around, what I'm going to do is I'm going to add another electron to my O2 picture to make O2-. So I'm going to add another electron into that anti-bonding orbital. So again, we still have our 8 bonding electrons. But as I mentioned, now what we have is we have 2 anti-bonding electrons here and another 3 up here. So this is going to be minus 5. I'm going to divide by 2, and what I get is 1.5 as my bond order. Now what you guys should remember is the higher my bond multiplicity is, or in other words, the higher my bond order is, the stronger my bond energy is. And the stronger my bond energy, the shorter my bond length. So in this case, what we see is that O2 plus has the highest bond order. So that means it has the highest bond strength or bond energy, and it has the shortest bond. In fact, experimentally, what we find is that this is the case. O2 plus is the strongest bond, O2 is the next strongest bond, and then O2 minus is the weakest bond. So again, this is something that we see experimentally and is predicted by MO theory. And again, this is something that we cannot tell from Lewis dot structure, VSEPR, or hybridization theory. So again, this is MO theory bringing explanation to our natural world. Well, I hope that made sense, Chem 1A, and remember to stay safe.